Hey guys, how's it going? This is Siri and I'm back with another calculus video. And in this video, we're going to be motivating the definition of a limit. We're not actually going to cover the definition of the limit, but we're going to, sort of introduce rates of change and, see it graphically, see it in a simple problem, and sort of motivate that definition of a limit. And we're not actually going to cover the formal definition of a limit in this video. We're going to do that in the next video, so stay tuned. Okay, so let's, sort of investigate rates of change through a simple example. Okay, so we have a car, right? It's traveling 100 miles in 2 hours, right? So we have a car. Let's say we have a car. It's traveling 100 miles in how much time? In 2 hours. Okay, and we are asking a simple question which you've probably already answered in previous math classes, right? How fast is this car going, right? How fast is this car moving? Or going, or whatever, right? How fast is it traveling? Well, we know that if we want to find how fast, we want a rate, right? We want rate equals literally how fast, how much is something changing per unit time, right? So in this case, it would be distance per time. And you've probably seen this formula before. Well, it's not really a formula, it's more like a definition, but distance per time, right? Rate equals g over t. How far did we travel? We traveled 100 miles. In how much time? 2 hours. So we get 50 miles per hour, okay? That is the rate, okay? And we are looking at rates of change in this video, so that's appropriate. Okay, let's look at a graph. Let's graph this, right? So we have a y-axis, we have an x-axis, x, y. Let's make this time and distance. So let's call it distance. And this is in miles. We know that. What is this going to look like graphically? Is it going to look like a curve? No, it's not going to look like a curve. It's going to be a line, right? It's going to be a line. And why is it a line? Well, in this particular problem, we have a constant rate. We have a constant speed, okay? And this is very important because we're going to look at things that are not constant in just a second. So this is constant. Constant what? Constant speed. Assuming that we're going in one direction, right? Which doesn't really matter in our situation, in our case, right? So we're at a constant speed, 50 miles per hour. At this instant in time, okay, let's do this here. At this instant in time, t, it's 50 miles per hour. And this instant of time, t plus 1, it's also 50 miles per hour. And this t plus 100, okay, forget about the units, right? It might be in seconds or something. Also 50 miles per hour, right? We're at a constant speed, okay? And so what does this line tell us? The slope is the speed, right? If the slope is change in y over change in x, right? We have a slope. This is speed, right? The slope is speed, and the slope is 50, right? 50 miles per hour. That is the slope. Okay, and so you already know this, right? I'm assuming, right? Because we're dealing with constant rates. So now let's change up the example a little bit. Let's say that the car still travels at 100 miles. Right, so example 2, or just a little tweak, still travels 100 miles and still travels those 100 miles in 2 hours, right? 100 miles We have 2 hours. But what's different about it? This time, it does not travel at a constant speed. Not a constant speed. And what does that look like, and what does that mean? Not a constant speed. Well, this is probably how you drive, or yeah, probably how people drive, right? Not at constant speeds. Right? So, for example, you probably graphically, like, it takes a while to start, let's say, okay? Let's say that it takes a while to start, and, so, like, the slope, which, as we said, is how fast you're traveling, the miles per hour, which is the rate, distance per mile, distance per time, right? So we slow down a little. Not slow down. It takes a while to start, so we're a little slow, but then we accelerate. We go a little quicker, and then we slow down to a stop. Okay? So we're a little slow here. We pick up the pace here, so it's a little faster. And then we slow down again. Right? That's sort of how it goes if we're not going at a constant speed. And so, right, okay. And so this is what the distance time graph would look like. Distance time. Okay, and so now we ask the question, not how fast is it going literally anywhere, which in a constant speed scenario, but how fast is it going at 1.5 hours, or hour, at 1.5, or 1.5 hours into the journey, how fast are we going, right? And so how do we answer that question? Well, first we need to understand what that question means. Well, and, you know, it might be confusing, right? If we've never studied calculus before, whenever we've been asked how fast something's going, we always have a point here, and we have a point here, and then we check out the slope, right? We have 2 points. We always do y1 minus y2, or the other way around, as long as we're consistent, x1 minus x2. We always have 2 points, right, when we look at the point slope formula, and, you know, just the definition of slope. So what do we mean when we're asking for the slope at 1 point? Right, so before we answer that question, let's just take it at 2 points, right? What we've always been doing, right? Let's take 2 points here, and, you know, at this 1.5. Let's just say that this is 1.25, right? And let's find the slope. Let's find the average rate, right? Average speed, okay? And so the average speed is essentially, we take 2 points and we connect them through a straight line, using a straight line, and we see what is that slope, and that's the average speed. That's the average rate of change between time equals 1.25 and time equals 1.5 hour. Right, so the average slope of the line connecting those 2 points is the average speed, regardless of whether the overall behavior is constant or not. Right, so that's what we mean when we talk about average speed. But in this case, when we're asking how fast is it going at 1.5 hours, we are only looking at 1 point. So let's try this. Let's say that this point here, say that this is point 1 and this is point 2. Point 2 is our goal. We want to really be there. Let's say that point 1 approaches point 2. And it gets closer and closer and closer and closer. Okay? And as it gets closer and closer, we get a more accurate, quote-unquote, instantaneous speed. Okay, so we have average speed, but we also have instantaneous speed. okay? And so that's what we're asking for at, when we ask, like, what is the speed at t equals 1.5, well, that's what we're asking for. What is the instantaneous speed at this time? Okay? And the value that we get, the value of the slope that we get, or the value of literally anything, like as we approach something and we get really, really close to that particular thing, we call that the limit. But we'll get into a more rigorous definition in the next video. But the main idea is that we get P1 as close as we possibly can to P2. Okay, and then the value of the slope gets closer and closer to the instantaneous speed. Okay, I think I'm gonna leave it at that for this video, and in the next video we will look at limits in more detail, and we will sort of tackle that in our next video. Okay, I hope you learned something new. I hope you got an idea for what rates of change are, what the average rate of change is, what, you know, sort of the instantaneous rate of change is, and you know, we'll dig into that in our next video. We'll dig into limits in our next video. Okay, all right, thank you so much, and I'll see you next time. Bye.